So in this example, we want to formulate how we're going to find binomial probabilities. So let's suppose that there's an 82% chance that any random flight at Midway Airport is on time. We're going to choose three flights at random. Yeah, free flights. We're going to choose 3 flights at random. Let x be the number of flights that are on time. It's going to be our random variable. Find the probability distribution of the random variable x. So first, is it binomial? So binomial, we need identical trials. We're choosing 3 flights randomly, so those are identical. We need 2 outcomes. The flights are either on time or late. Probability of a success, so probability on time needs to be the same, and it is 82% for any random flight. And then trials are independent. Now that one, some plane flights are independent of each other, but if you got a connecting flight, a flight, if a flight's late, it can make a connecting flight or a following flight late after it. So this may not be completely independent, but we'll analyze it as a binomial. So binomial here, almost. In most cases, it would be binomial. So let's analyze this using a tree diagram. So that first flight could either be on time or late. So on time is success, late's a failure. If the first flight's on time, the second one could be on time or late, success, failure. If the first flight's late, the second one could be on time or late. And then same way for the third flight, it's going to be the third level in the tree. We have a success failure split off of each one of those. And then remember, we put the probabilities on the branches. So probability of a flight being on time, that success is 82%. So that leaves 18%. 1 minus 0.82 for the failure, and it's that way on all the branches here because these flights are independent for the most part. And then we can go ahead and list our outcomes and start finding probabilities. So our outcomes, we follow the branches down, success, success, success. So 3 S's. Success, success, failure, SSF. Success, failure, success, SFS. SFF, so first flight on time, the other 2 late. Failure, success, success, and so on. So we've got FSF, FFS, and 3 late flights. So then remember, we multiply on the branches here. So this one's going to be 0.82 cubed. Here 2 are on time, so that's 2 0.82s and 1 0.18. So 0.82 squared times 0.18. And then 2 0.82s there, 2 successes, so that's a 0.82 squared. 0.18. Only 1 on time there, so 2 0.18s, so that's a 0.82. 0.18 squared, and then 2 that are on time there, so that's back to the 0.82 squared, 0.18, 1 on time, so 0.82, 0.18 squared, again 2 late and 1 on time, and then 3 that are late would be 0.18 cubed. So we can compute all these in the calculator. So if you do on that first one, you will get 0.5514. On that second one, 0.1210. Another 0.1210. So all these ones that have 0.82 squared be 0.1210. It should be 10. And then let's see, the 2.18s, that's a 0.0266. And here also, and here. And then the 0.18 cubed is 0.0058. Now if you sum all of these up, those are all of the outcomes for the experiment, we get approximately 1. Should get approximately 1 all the time. So now we want to know, what are the probability of 0 flights on time? Well, there's only one way that occurs. All 3 are late. That probability is 0.0058. And again, that comes from the 0.18 cubed. So this is actually the 0.82 here gets a 0 power, and then the 0.18 is cubed. And then there's one possibility like that. Probability x equals 1, so 1 flight that's on time. So 1 flight on time, let's circle those with red here. So we've got 1 success here, and here, and here. So we've got 3 possible ways that we can have 1 flight on time. And each one of those is 0.0266, which is 0.82 times 0.18 squared. And that is 0.363. And then 2 flights on time. So let's circle those in black. So that's here. We had 2 S's here and here. So there were 3 ways that that occurred. And they're all 0.82 squared times 0.18. Oh, and I'm sorry, this is the 0.363. This one up here is actually 0.798. And then probability of having 3 on time, that's just this one sample point. That's the, there's one way to do that, and each one is 0.82 cubed, which is 0.5514. And these 4 numbers also total to 1. So we can look at that probability distribution. Now, the 1 here and the 3 and the 3 and the 1, they have a special significance here. There was one way to choose 0 flights on time out of 3. So this is 3, choose 0 is what that is. And then there is 3 ways to choose the 1 flight that's on time. So this is 3, choose 1. And then there are 3 ways to choose 2 flights on time. So that's 3, choose 2. And then there's only 1 way to choose 3 flights on time. They're all 3 on time. So this is 3, choose 3. So we're seeing that pattern, and then we're also seeing, notice the exponent on 0.82 starts at 0 and then goes up, and the exponent on 0.18 starts at 3 and then goes down. So the general pattern of what is going on there is the following. So in general, we've got this binomial probability formula here. So the probability of x successes, so n is your number of trials, x is successes, and p is the probability of success for one trial. So the probability of x successes, so here 0, 1, 2, 3, is n choose x, so total choose out x, that's choosing which ones are going to be successful, p to the x, 1 minus p to the n minus x. So that's the general pattern that we can get for all of these that we're seeing there. Where your n choose x is combinations of x from n, or n factorial, x factorial, n minus x factorial. So that is the general pattern that we're seeing.